Question 2 says let f of x equal 2x e to the 2x, a function defined for all real numbers. Evaluate the limits of f of x as x approaches negative infinity and x approaches infinity. So when you're doing these questions, there are a couple of limits that are really helpful to know. In this case, it's what happens as e to the x approaches infinity and negative infinity. As x approaches negative infinity of e to the x, you're getting closer to 0. And as x approaches infinity, well, you're constantly increasing. So we'll say it's always getting closer to infinity. Okay, so with those in mind, let's come over here and let's see if we can figure out what the answers are. Now, when we're doing these, what I like to do is I like to split this up into pieces here. So for example, we've got the 2x piece here, and then that is being multiplied by the e to the 2x piece. And what I do in my head is I look at each piece individually to see what's happening. You can see I'm kind of doing both of these at the same time, but I'm just going to focus on this problem first, and then we'll come to this one next. So as x approaches negative infinity here, we have 2 times, well, a very negative number. So we're always going to be getting negative numbers that are always increasing toward negative infinity. On the other hand, e to the 2x is just like what we have over here, right? X is approaching negative infinity. It's e to the 2x instead of x, but that doesn't change the fact that this is always getting closer to 0. So you could think of this first piece as like negative infinity times 0, which gives 0 as our answer. Now let's do the same thing for x approaching infinity. As 2x approaches, or if we take 2x and let x approach infinity, this will just continue to increase toward infinity. The same thing will happen with our e to the 2x, just like our limit over here, which means that, on the whole, the entire thing is always increasing. And so these are our answers. Part B says determine the absolute minimum value of f of x and justify why it is the minimum. Well, anytime you're asked about minimums or maximums, probably the very first thing you're going to want to do is use the first derivative test, which is what we're going to do here. Now, as part of the first derivative test, you are going to be finding critical numbers. Now, when you find critical numbers, there are 2 things you have to do. Most students remember the first one, but a lot of students actually forget the second one. The first one is you find the derivative and set it equal to 0 and find out what makes it equal to 0. The second one is you take the derivative and you find where it does not exist. Now, as it just so happens in this problem, we will not have to worry about this, which is probably why everyone remembers the first one so well, because there are quite a few questions where you don't have to worry about it. But do keep it in mind, there definitely are questions where you have to do this in order to get the right answer. With that said, let's go ahead and find our first derivative over here. We're going to need to use the product rule. So that means we're going to need the derivative of 2x times the second piece plus the derivative of the second piece, which requires the chain rule, e to the 2x times the derivative of 2x times the first piece. And because we're going to be setting these equal to each other, or excuse me, we're going to be setting this equal to 0, let's go ahead and factor. So we have 2e to the 2x times 1 plus 2x. See, now that we have it factored, we can set each of these equal to 0. And you'll see that in this first piece over here, we won't be able to find at least any real numbers that make this equal to 0. But over here, we certainly can solve for x, right? Subtract 1, divide by 2, we get negative 1/2. All right, now before we go further, there are a couple of things that I want to point out because these are important. When you're using the first derivative test and when you find your critical numbers, what you are going to be finding are the local minimums or local maximums. In this problem, they specifically ask us for the absolute minimum. So we're going to have to justify why that is the case in just a second here. But first, we need to even make sure it is a minimum. Perhaps it is a maximum. Now, I doubt that just because of the way the question is worded, but you never know for sure. So here's what we're going to do. We're going to draw a number line. And then on this number line, we are going to put a couple of test values, or test numbers, maybe I should say, like this. So these test numbers are going to be plugged back into the first derivative. And then what we're going to do is we're going to see if we get positive or negative answers. So let's come all the way over here to the left side. We're going to take -1 and we're going to plug it in. And then after that, we're going to take 0 and plug it into our first derivative. Now take a look here at our factored version of the derivative down here, the one that we set equal to 0. At the beginning, this first piece is 2e to the 2x. And as it just so happens, no matter what value you plug in for x, you will always get a positive answer here, which is in fact why this couldn't be set equal to 0. So, in other words, this is always positive. So over here, I'm just going to write a little plus sign. And you see, it doesn't matter if we're plugging -1 or 0 or a million in, this will always be a positive answer. This second piece, however, will not always be positive. It is determined by the test numbers that we plug in. So if we plug -1 in here, we're going to get 1 plus -2, which is a negative answer. And of course, a positive times a negative is a negative. So up here, I'm going to write negative. Now, when we plug 0 in, this is just going to turn into 1 plus 0, which is 1, which is, of course, positive. And a positive piece times a positive piece is positive. So up here, I'm going to write positive. Now, here's the important part with the first derivative test. If you have a negative first derivative, that means your function is decreasing. So perhaps it's doing something kind of like this. Then we have, of course, the -1/2 point. And then after that, the function will be increasing because that's where the derivative was positive. So you can see here that x equals -1/2 definitely does give us a local minimum. Now, here's another important thing. -1/2 is not the local minimum. It is where the local minimum occurs. So the local minimum occurs at x equals -1/2. But what is the actual local minimum? Well, in order to figure that out, we have to take this and plug it back into the original function from the beginning. So let's do that. I'll do that over here. Now let's see here. We are plugging -1/2 in. We're going to plug that in for x. Let's see what happens here. Now you can see that we have this 2 times -1/2 showing up twice. In each case, we're going to get -1. And if we simplify this a little bit, we get -1 over e. So the local minimum occurs at x equals -1/2, and the local minimum is -1 over e. Okay, so we have figured out what the local minimum is. We figured out where it is. Is that the absolute minimum? Well, as it turns out, yes, it is. And that's because of this number line that we've set up here. Notice that we had a function which was always decreasing. Then we had one of our critical numbers that we found. And then thereafter, the function was always increasing. So if the function is always decreasing and then always increasing, that must mean this is the only point that is as low as it can possibly go. Or in other words, that is the absolute minimum. So if we're going to write out our answer here, we might say something like this. Since f prime of x was negative for x being less than -1/2, and since f prime of x was positive for x greater than -1/2, right, everywhere to the right of it, let's see here. The point -1/2, -1 over e, must be an absolute minimum. And there we go. We now have our answer. Part C says find the range of the function f of x. Now, one way of thinking about the range is thinking about all the y values that you can get from a function like this. And actually, what we're going to do is we're going to use what we learned from Part A and Part B to help us with this. Remember that in Part A, we figured out that the limit as x approached infinity of our function was infinity. And the limit as x approached -infinity of our function was 0. Then in Part B, we figured out that the absolute minimum occurs at this point here. It was -1/2, -1 over e. So we can actually do a quick little sketch of what I've got here. Here we go. So let's say that this is -1/2 here. And then let's say this is negative 1 over e over here. This will be our absolute minimum. Now, another thing I'm going to do is I'm going to draw a little asymptote here, a horizontal asymptote, because as x approaches negative infinity, we are getting closer and closer to 0. And then, as x approaches positive infinity, well, we're just going to be going up forever here, right? We got infinity here. And then there's our lowest point. So if we're trying to find the range, and we're thinking about all the y values, and I've done a little sketch here, the lowest point that the graph ever gets is negative 1 over e, which we have to include. And then the graph just goes on forever upwards. So the range is going to be negative 1 over e, comma, infinity. Part D says, consider the family of functions defined by g of x equals ax e to the ax, where a is a non-zero constant. Show that the absolute minimum of g of x is the same regardless of the value of a, as long as a is not equal to 0. So this is an interesting question because up here they obviously chose 2, right? 2x e to the 2x, but they could have chosen a million x e to the 1 million x, and apparently we would have gotten the same absolute minimum. So here's what we're going to do. We're going to take our new function, g of x here, which is ax e to the ax. We're going to find the derivative of it using a. Well, a is a constant here, so we're just going to treat a like we would any other number. So the derivative of ax is a. Then the derivative of e to the ax will be e to the ax times the derivative of ax, which is just a, times the first piece. Then what we'll do is we will sort of like simplify this like this, get rid of the parentheses. A times a is a squared, move the x up front. We'll take an a e to the ax, so we'll factor that out. Then we'll set these equal to 0 like we did in one of the previous problems here. This first one here will not be possible, but this one is possible. If we subtract 1 and divide by a, we get negative 1 over a. Then what we're going to do is take negative 1 over a and plug it back into our original function. So g of negative 1 over a. So let's see what happens when we do this. Negative 1 over a. Okay, so a times negative 1 over a is negative 1. We get the same thing up here, negative 1. And if we simplify it, we get negative 1 over e, which you'll notice is the same answer we got from before. So indeed, it does not matter what constant you use here, you would have always gotten this as your absolute minimum.
If you found this video helpful, you might consider checking out my website, which is linked in the description below. You'll be brought to Infinity Learning Academy, where you can find Cruising Through Calculus. At Cruising Through Calculus, we have over 100 videos and documents to help you get through your calculus class, including videos for each topic, practice problems, and full video solutions for those practice problems. I hope to see you there, and together we can cruise through calculus.